Good evening, everyone. I welcome you all in this live session 4. So, it is a third lecture in line with steam power systems. So, today we will talk about all those turbine, boiler, and condenser, and we'll solve the assignment 4 from the previous year course. Okay, so let's start this session. So, uh, in the last session, we discussed about the steam power system as a whole, then steam power cycle, and we analyzed the whole cycle, the thermodynamic aspect of the steam power cycle, and solved the related problems as well. Uh, so, this is the typical steam power cycle we discussed about in the last couple of lectures. So, to recap, so once the water is fed into the boiler, it is at low temperature and high pressure coming from the pump. In boiler, the heat is being transferred to the water. The Q1 heat is being transferred to the water. Then the water becomes high temperature and high pressure steam. Then it goes to the turbine where we received work WT, and steam exited the turbine at high temperature and low pressure. Then it goes to the condenser. It condenses into the water, and the state is low temperature, low pressure, and heat Q2 is rejected to the atmosphere or cooling water. Then this low pressure, low temperature condensed water is fed to the pump, and again the low temperature and high pressure condensed water is fed to the boiler. That's how the circle is completed. Okay. Now, now what are the components here we are talking about is the mainly the turbine, condenser, boiler, and pump. Okay, so today we will talk about turbine, boiler, and condenser. What are the types of these turbine, boiler, and condenser, how they work, what is the working principle, and what are the main uh, component. Okay, so if we talk about the turbines, there are two types of turbines: the impulse turbine and reaction turbine, and also the another uh, main part of the turbines is nozzles. So we will talk about all those three: impulse turbine, reaction turbine, and nozzles. Also, the other component is boiler. So boilers are also of two different types. One is fire tube boilers. The second is water tube boilers. We will look these two as well, and then comes the condenser. So we will talk about direct contact type condenser and surface condenser as well in this session. Okay, so starting with the turbines. So there are two type of turbines: the impulse turbine and reaction turbine, and these are the working principle of these two turbines is different. In the impulse turbine, the all the pressure is dropped in the nozzles only, and then from the nozzles comes out is a high velocity steam jet, and this high velocity steam jets impinges on the moving blades, transfers the momentum to the blades, and this transfer of the momentum or impulse principle is solely responsible for the energy transfer to the moving blades, thus to the shaft, and then we get the turbine work WT out of the shaft. Okay, but in the case of reaction turbines, the whole pressure is not drop in the nozzle, but the partial pressure is drop in the nozzles and the remaining pressure drop in the moving blades as well. So when the pressure drops in the moving blades, then due to the drop in the pressure, there is a reaction from the steam coming out from the blades. Due to this reaction, a force is exerted on the moving blades. So the total energy that is transferred to the moving blades is because of the high velocity steam jet coming out of nozzles, as well as the reaction of the expanding steam going out from the moving blades. So because of nozzle, because of high velocity steam jet and the reaction, so both are there, that's why it is called as impulse reaction turbine. But to distinguish from the impulse turbine, it is simply written as reaction turbine. Okay, so actually the reaction turbine is impulse reaction turbine because it consists of the work we get from reaction turbine consists of the work transferred through the high velocity steam jet, as well as the expanding steam, the reaction from the expanding steam coming out from the moving blades. Okay, so the main difference here is when the pressure is being dropped. So in impulse turbine, the whole pressure is dropped in the nozzle itself, and in moving blades there is no pressure drop. And in reaction turbine, the partial pressure drop occurs in nozzles and the remaining pressure drop occurs in moving blades. Okay, so this is the main difference. And the work transferred in the case of impulse turbine is due to impulse effect of the steam jet only, but in case of reaction turbine, the work done is due to impulse effect plus reaction force of exiting steam coming out from the moving blades. Okay, and in the case of impulse turbine, as the whole pressure is dropped in the nozzle itself, the steam velocity, the jet velocity coming out of uh, the nozzle is extremely high, as well as the blade velocity is also very high. But in the case of reaction turbine, as the whole pressure is not being dropped in the nozzle itself, so the jet velocity is low compared to the impulse turbines, as well as low, this blade velocity is also low. Okay, so these are the main and basic differences between impulse turbine and reaction turbine. So here in the figures you can also see, in the first figure under this impulse turbine, you can see here only the steam is going through the nozzles, and here you can see in the graph, so the yellow lines shows the stream pressure and green line shows the steam velocity. So in the case of impulse turbine, the pressure is dropped in the nozzles itself. So pressure from here to here drops in the uh, nozzles itself, and the result of this pressure drop is the velocity of the steam increases in the nozzle itself. And then we can see in the moving blades there is no pressure drop, but the steam velocity drops continuously. So it shows that the pressure drop occur in the nozzle itself and no pressure drop in the moving blades. But you can see in the case of reaction turbine, the pressure drops in the nozzles from this point to this point. The result of this is the velocity increases from this point to this point, but as the steam moves to the moving blades, the pressure still drops in the moving blades from here to here, as well as the velocity is also dropping from here to here. So this means in the reaction turbines, in the moving blades, the velocity is also decreasing as well as the pressure is also decreasing. So the total work received on the reaction turbine shaft is because of impulse effect of the high velocity steam jet as well as the reaction force of the expanding steam exiting the moving blades. Okay, so this is the main and basic difference. And one another term here is degree of reaction, R. Okay, so degree of reaction is defined as uh, the ratio of the enthalpy drop in the moving blades divided by total enthalpy drop. So total enthalpy drop consists of enthalpy drop in fixed blades. So in reaction turbines there are fixed blades that works as nozzle, but in impulse turbine there are nozzles itself that works as nozzle. Okay, so the fixed blade means for impulse turbine it is nozzle, for reaction turbine it is fixed blades that works as a nozzle. Okay, so this is how degree of reaction is defined. So it is a ratio of enthalpy drop in moving blades and the total enthalpy drop. So in so for the case of impulse turbine, del H moving blades will be 0 for impulse turbine, means R, the degree of reaction is 0 for impulse turbine, but for reaction turbines this del HMB, that is enthalpy drop in moving blades, will be a non-zero term. And how much it can be? The del H can be uh, uh, this can be the value of R varies between 0 to 1. So it is 0 for uh, impulse turbine and 1 for fully reactive turbine, full reaction turbine. And the in general the value of degree of reaction varies from 0 to 1. Okay, and the next is that was the basic difference between both the turbines. The next thing is nozzle. So nozzle is a variable area passage to a fluid that helps in converting the heat energy or pressure energy into the kinetic energy of the fluid. Okay, so before looking at the nozzles, first what is the sonic velocity in a fluid? So the sonic velocity in a fluid depends on its pressure and density. Okay, so here you can see the sonic velocity C is equal to under root of del P by del rho. So it means, yeah. So in the fluid, sonic velocity is the function of pressure and density, and there is another term that is Mach number, and Mach number is defined by so for a fluid at some velocity v, the Mach number is defined as v by c, where c is the sonic velocity. So the ratio of velocity and the sonic velocity is called as Mach number. Now, for a flow through a nozzle. So for a flow through nozzle, we can write this equation. I think you have already watched the videos by Mondal sir. So in those videos, he has explained very well how to arrive at this equation. So for a nozzle flow, this equation shows the relation between the change in area and change in velocity, and both are connected with the Mach number. So here from this equation 1, you can see if there are two cases, if the Mach number is less than 1 or Mach number is less greater than 1. So in the first case, when Mach number is less than 1, so what it mean by Mach number less than 1 is the velocity of fluid is less than sonic velocity. Okay, so that is called as subsonic flow. So for a subsonic flow, here you see this term m square minus 1 becomes less than 0. Okay, so this becomes less than 0 means it is negative value. Now if we see from here, dA by A is equal to minus some value k dV by V. So for a subsonic value, if your area is decreasing, if dA is negative, okay, then the change in velocity should be positive. It means if the area is decreasing for a subsonic flow, then the velocity of the liquid or fluid will increase. Okay, so we can say for a subsonic flow, the converging passage means the area is decreasing continuously, so the converging passage will work as nozzle because the velocity increasing. So in a nozzle, velocity increases at the cost of heat or pressure drop, and in diverging passage, that is called as diffuser for subsonic flow. In diffuser, the uh, velocity decreases at uh, the loss of pressure or heat energy. Okay, so here to reiterate it, for the case 1, that is subsonic flow, the velocity is less than sonic velocity, Mach number less than 1. uh, this m square minus 1 becomes less than 0, that means it is a negative value. Now dA by A is equal to minus some value k into dV by V. So for a converging passage, the dA area is reducing continuously, that means that is a negative value of dA. For negative value of dA, the value of dV should be positive according to this equation. So for a converging passage, for a subsonic flow, that will work as a nozzle. But similarly, if we consider a diverging passage where the area is increasing, means dA is positive, in that case the value of dV should be negative to balance the equation. Means for a subsonic flow, a diverging passage works as a diffuser. Okay, I hope you got it. Now now this we see the second case. So the second case is when the value of m is greater than 1, means the velocity of fluid is higher than the sonic velocity, that is called as supersonic flow. Now for supersonic flow, this value of m square minus 1 is greater than 0, that means dA by A is equal to some value k dV by V. Now if we consider a converging passage means area of the passage is continuously decreasing, means dA is negative. So for a negative value of dA, the value of dV should also be negative. That means for a converging passage, for a supersonic flow, that will work as a diffuser because the velocity, as the area decreases, the velocity is also decreasing. Okay, but if we consider a diverging passage, so what diverging passage means, the area is continuously increasing. So in the case of diverging passage, the dA is positive, and to balance the equation, the dV should also be positive. Means for a supersonic flow, a diverging passage will work as a nozzle. Okay, so this is the basic concept about flow through nozzles. Now see in the figures. So when a nozzle is designed for a supersonic velocity of exiting stream jet, we consider these two cases where when the velocity of the fluid is subsonic, we use a converging passage so that the velocity of steam continuously increases. And when at a point, here in the figure you can see, uh, here in the figure you can see at this point, the third figure you can see, at this point when the velocity of the steam or fluid uh, becomes the sonic velocity, means m becomes is equal to 1, the sonic velocity, then the next part of this nozzle is the case second, where the supersonic velocity, we are achieving the supersonic velocity, and a diverging passage works as a nozzle. So in the case of this third figure C, you can see the first, when the velocity of fluid is less than sonic velocity, means it is a subsonic flow, we are using a converging passage that works as a nozzle. At this point, middle point, the velocity becomes sonic velocity, and to go further we are using a diverging passage that works as a nozzle for supersonic flow. So here, once the steam enters at a subsonic velocity, it achieves it achieves the sonic velocity at this point, and then further it moves through the diverging passage that works as a nozzle for supersonic flow, and the velocity further increases. Okay, so that's how a nozzle works. Okay, so this is the like basic principle of nozzle working. And now here is a point that when this fluid achieves the sonic velocity at this point, uh, this is the situation when the Mach number becomes 1, the fluid gets the fluid achieves the sonic velocity, and the mass flow is the maximum, and mass flow cannot be increased uh, above this point. So this type of flow is called as choked flow. So this point here in the middle is choked now. The mass flow rate cannot be increased beyond this point, and this point is called as throat. Okay, so in a nozzle flow, at the throat, Mach number becomes 1, mass flow rate becomes maximum, and this is called a choked flow. Okay, so this is we talked about turbine and nozzle. Now the next uh, component here is the boilers. Okay, so the basic function of boiler is phase change. The liquid water is fed into the boilers. A heat Q1 is transferred to the this liquid water to vaporize it into the steam, and this whole phenomena takes place at a constant pressure. Okay, so ideally it should be at constant temperature, but for steam power cycle, the temperature doesn't remain constant but pressure remains. Okay, so basically if we say it again, in boilers the phase changes from water to steam at a constant pressure. Okay, and the second part here is the superheaters. So in the boilers the steam is the water is converted into the steam, and the steam exits the boiler at saturated steam point. From there, the temperature of steam is further increased by transfer of heat to a superheated state. Okay, so in superheaters, a saturated steam temperature is increased by transferring the heat, and the amount of heat that takes place, the amount of heat transfer that takes place into the superheaters is around 40%. Okay, and we all know, and in the previous sessions we discussed about it, that superheating the superheating of steam results in the overall cycle efficiency increment. Okay, so that is the main reason uh, for superheating the steam before the turbine, and also it improves the quality of the steam at the turbine exit. We all studied and discussed about that in last couple of lectures. Now, so what are the types of boilers? So based on the working principle, the boilers are mainly of two types: the fire tube boilers and water tube boilers. As name suggests, fire tube boilers means the hot gases coming from the combustion of fuel flows through the tubes, and the surrounding water gets heated and steam comes out. And in case of water tube boilers, the hot gases that are the product of burning of fuel, uh, these gases flow around the tubes and the water flows from the tubes. Okay, so in the first case, these hot gases flows through the tube, and in the second water tube boilers, the water flows through the tubes and heat transfer takes place from the hot gases that are around the tubes. Okay, but both works differently, as in the fire tube boilers the chamber is very big, and the quantity of water is much more than the water tube boilers, so it takes a lot of time to generate heat. But in the case of water tube boilers, the heat generation takes place in a less time. For fire tube boilers, the rate of heat generation is lower compared to the water tube boilers as well. And also the fire tube boilers uh, works at a low pressure up to 20 bar, but in the case of water tube boilers, these works at high pressure up to 200 bars. Okay, so these are the two main type of boilers, and they are like the differences between these boilers. And the next part is the condenser. Okay, so till now we talked about the turbine, both type of turbines and the nozzles, and also boiler and superheater. Now the third main components, that is the condenser. So in the case of condenser, so one thing comes to the mind is, why do we need a condenser? Why don't we reject the steam coming out from the turbine and feed a fresh water uh, through the pump to the boiler? So this is because the first reason is we need to complete a cycle. As from the second law of thermodynamics, we know to get a net output, there should be two uh, two temperature bodies, hot body and cold body. Between these two bodies, a cycle should work to get a net work output. Okay, and this is a closed cycle, so to complete this closed cycle we need a something where we can reject a heat q2. Okay, so this something is condenser first. And the second reason to use a condenser is, if we use a condenser, we can increase the specific output from the turbine. How? You can see in this figure. So if we expand the steam to the atmospheric pressure, that is at 1 atmospheric pressure or 1.013 bar, so in that case we achieve this work. You can see in the hashed area we receive this work, but but the steam condenses at 100 degrees centigrade at atmospheric pressure. Okay, that we all know. But as we use a cooling water, that is at atmospheric water, suppose that is at 40 degrees centigrade. So if we are exiting the steam at atmospheric pressure, then we have to exit that steam at 100 degrees centigrade. But if we are using a condenser, we can further expand this steam to a point where that is corresponding, that saturated pressure that is corresponding to the temperature 40 degrees centigrade. Okay, and that saturated temperature, saturated pressure is 0.074 bar. Okay, so if we expand this stream to this point, then this hatched area in the green is increased. So we can say, if we can expand the steam to a to the atmospheric temperature in some way, then we can increase the specific output of the turbine. Okay, so to achieve this higher specific output of the turbine, we use condenser which operates at a pressure lower than the atmospheric pressure, and that pressure is corresponding to the atmospheric temperature, corresponding condensing condenser temperature, uh, or saturated temperature corresponding to the atmospheric temperature, that is 40 degrees centigrade that time. Okay, so these are the two main reasons we use a condenser in the steam power cycle. Okay, now now how many types of condenser are there? So mainly condenser are of two types. The one is direct contact type condenser and second is surface condenser. And these two types are further divided into many types of condenser. That is not the scope of this session. So in direct contact type condenser, as the exhaust steam comes, a cooling water mist is inserted into the chamber. So this cold water mist and exhaust steam mixes together, and we get a condensate, that is uh, that is the cooling water plus condensed steam. Okay, so this kind of condenser is called as direct contact type condenser. But in indirect of surface condensers, the mixing of exhaust steam and cooling water doesn't takes place. They are separated by a wall, and that is a tube wall. So in the case of surface condenser, a cooling water is flows through the tubes, and exhaust steams comes, flows over the tubes, and heat transfer takes place between the cooling water and exhaust steam through the tube surface. Okay, so that's why it is called as a surface condenser. So this is the basic summary of turbine, boiler, and condensers that you have already watched in the videos. So based on this summary and the videos you have already watched, we will try to solve some of the problems from the previous assignments. So the first question here is, the degree of reaction of an impulse steam turbine is. Okay, so here we know the degree of reaction is defined as del H moving blades divided by total enthalpy drop. Okay, so in the case of impulse turbine, delta H mb, that is enthalpy drop in moving blades is 0. Okay, because all the enthalpy drop takes place in the nozzle itself. So in moving blades there is no enthalpy drop. That means the numerator is 0 and the degree of reaction R becomes 0. Okay, so B is the answer. And I think Vicky and Priyanshu, your answer are correct. This is 0. Okay. Now the next question is, in Mollier diagram, constant pressure lines blank space from one another, and that is a maintain equal distance, diverge, converge, or nothing can be said. Okay. So here, what is a Mollier diagram? Mollier diagram. So Mollier diagram is HS diagram, enthalpy entropy diagram, and how these Mollier diagrams looks like. These looks like as in this figure. Okay, so this is the diagram between enthalpy H and entropy S, and here you can see three type of lines. That is, one is blue lines. These blue lines are constant pressure lines. The second one is green lines. These green lines are constant temperature line. And then third one is red lines, and these red lines are constant steam quality line. Okay, and this dark red line is the saturation line. Okay, now we are asked about, in Mollier diagram, constant pressure lines from one another, what happens? Do they converge, do they diverge, or are they parallel? So from this figure we can see these blue lines, as we are going forward, these blue lines are the distance, the distance between two constant pressure lines is increasing. So that means these constant pressure lines are diverging, and that can be clearly seen in the second figure. Here these constant pressure lines are diverging. And why do they diverge? Because as the pressure increases, the saturation steam temperature also increases. That is the reason behind the divergence of these constant pressure lines in the Mollier diagram. Okay, so what is the answer? The first is wrong, third is wrong, fourth is wrong, and second one is right. Okay, so these constant pressure lines diverge from each other in the Mollier diagram. Any doubt in this question? Okay, so now move to the third question. It is, if at the inlet of a turbine the water possesses kinetic energy as well as pressure energy, the turbine is known as reaction turbine. Okay, so as we have already seen in the impulse turbine, so in the impulse turbine all the pressure drops in the nozzle itself, but in reaction turbine this pressure drops partially in nozzle and partially in moving blades. Okay, so here the question says, at the inlet of turbine the water possesses kinetic energy. Kinetic energy means high velocity jet. Okay, kinetic energy means high velocity jet, and as well as pressure energy. Okay, so in the case of impulse turbine all the pressure drops in the nozzle and it converted into the kinetic energy only. So in the case of impulse turbine, uh, there would be no pressure energy at the inlet of the turbine. Okay, but in the case of reaction turbine, the pressure it drops partially in the nozzle and partially in the moving blade. So in the case of reaction turbine, at the inlet there should be some pressure as well as kinetic energy. Okay, and the question is saying water possesses kinetic as well as pressure energy. The turbine is called as reaction turbine. That is the true option. Okay, because at the reaction turbine inlet there should be both kinetic energy, because the partial pressure is dropped in the nozzle, that converts that pressure and energy into the kinetic energy, and the partial pressure that is being dropped in the moving blades is also there in the form of pressure energy. Okay, so this statement is correct. Okay, so Priyanshu says it is false. No, Priyanshu. Earlier you got it correct. This is a true statement, because at the inlet of reaction turbine there is kinetic energy as well as pressure energy. But at the inlet of impulse turbine there will be only kinetic energy and no pressure energy. Okay, so this is the right option. Okay, now move forward. The question is superheating of steam in the boiler is done at. Okay, so so the question is superheating is happening in the boiler at this process is what, like constant volume, entropy, temperature or pressure. Okay, so from this figure, the which part of this figure shows the superheating? So this red red line wala part, this shows the superheating of steam, and you can see during this superheating process the entropy is not constant. Okay, entropy is increasing, so this option is wrong. Temperature is also not constant, temperature is also increasing, this is also wrong. Volume is also not constant in the case of this, but pressure remains constant, because this is the constant pressure line that comes from here to here, here and here. Okay, so this red line is the constant pressure line, and the superheating of steam in the boiler happens at constant pressure, but temperature doesn't remain constant, the temperature also increases. Okay, yeah. So the constant pressure, option 4 is right. Okay, any doubt? Okay. So now move to the next question. That is, fire tube boilers are blank space, while water tube boilers are blank space. Okay, and the options are low pressure, high pressure, low pressure, both high pressure and both low pressure. Okay, so as in the summary before, we saw that in fire tube boilers, that are the boilers in which the product of the combustion combustion products or the hot gases flows through the tubes, and it heats the water surrounding those tubes in the big vessel. Okay, so these fire tube boilers are low pressure boilers, and pressure goes up to 20 bar, right? While the water tube boilers are high pressure boilers, and pressure goes up to 200 bar, we saw in the last few slides. Okay, so it is a fire tube boilers are low pressure boilers, and water tube boilers are high pressure boilers. So option 1 is correct, others are wrong. Okay, and yeah, Vicky, you are right. I'm glad you remember. uh, So the fire tube boilers are low pressure boilers. The steam pressure goes up to 20 bar, but in the case of water tube boilers, the pressure goes up to 200 bar, and those are called as high pressure boilers. Okay, there should be no doubt in this question. If you have any doubt, you can ask. You can stop me midway at any question if you have doubt. Okay, so let's move to the next question. In condenser, heat is dissipated mainly by. Okay, so that is how the heat is dissipated in condenser. That is the question. And what are the mode of heat transfer? So mode of heat transfer is radiation, convection, conduction, and evaporation is not a mode of heat transfer. So that we won't talk about. So when the radiation happens, when the convection happens, and when the conduction happens. Okay. So in the case of solids, conduction happens. Okay. Even in the case of fluids, uh, conduction happens initially at a surface, and then the convection starts. Okay, and the convection is prevalent in fluids, and radiation prevalence at very high temperatures, and radiation doesn't need any of the any medium for heat transfer. Okay, so these are the three ways in which the heat is transferred. So in the case of condenser, where only the fluid exchange the heat, so the main way of heat dissipation is convection in the case of condenser, and radiation, as we know, is prevalent at very high temperature, and radiation is given as sigma e some t raised to power 4. Okay, the rate of heat transfer by radiation is given by this, and as you can see here, the rate of heat transfer is proportional to the fourth power of temperature. That means at very high temperature, this rate of heat transfer is very prevalent by radiation, but at lower temperatures, this heat transfer by radiation is even negligible. We do not even consider that. Okay, but in the case of condenser, heat is dissipated mainly by convection, and conduction is also there, but radiation is even not there. Okay, because at those low temperatures, the value of dq for radiation is negligible, and we consider it as zero. Okay. Okay. Priyanshu asked, okay, impulse staging is commonly employed in high pressure part and reaction staging in intermediate. Okay. Okay. I expect this question is not from the current assignment, because I cannot answer any question from the this current assignment. Okay. So. If it is from the current assignment, you have to solve it, you have to submit it, and then you can get back to me if you do not understand how this answer is correct. Okay, so but till then I cannot answer it. Okay, Priyanshu, I hope you understand, because this is in the current assignment, and it is expected that you solve with your understanding this question. Okay, so I would advise you, you solve it, you submit it, and if you don't understand, then you get back to me, I will explain it well. Okay. Yeah. Okay, so this is it, and the next question is, yeah, so the next is nozzle is choked when. So we talked about the choking. in the last few slides. So choking occurs when the Mach number 1 is achieved or the fluid velocity becomes the sonic velocity, okay, at the throat. This is the throat, and the flow becomes maximum. And at the throat, when the flow becomes maximum and the Mach number becomes 1 or the fluid velocity becomes the sonic velocity, at that point all the properties are called as critical properties. So pressure at that point is also called as critical pressure and temperature as critical temperature. Okay, so here we see the options. Nozzle is choked when discharge flow into atmosphere, no. Flow through is zero, no. Flow through is maximum, yes. And pressure is critical, yes. So option 3 is right. Okay. So it is a very conceptual question. We already discussed about it. So let's move to the next question. That is the steam nozzle converts. So what a steam nozzle does? A steam nozzle converts pressure or heat energy into kinetic energy, right? In the form of high velocity jet, right? So here is the options. Heat energy into kinetic energy, yes. Heat energy into potential energy, no. Kinetic energy into potential, no. Potential into heat energy, no. Okay, so steam nozzle converts heat energy into the kinetic energy. Now the next question is, exergy analysis is based on the second law of thermodynamics. Yes, we talked about exergy analysis in second law of thermodynamics. That is right. Okay, so we already discussed about this thing in the past few sessions, but to reiterate it, the first law talked about the quantity of energy, and the second law talks about the quality quality of energy, right? And here exergy means maximum obtainable work in a given environment, right? Okay, so in the first law we talked about the quantity of energy, how much heat is being transferred, net heat transfer should be equal to the network transfer. We talked about all those things in the first law of thermodynamics that consider the quantity of the energy. But in the second law of thermodynamics we always talk about the quality of the energy, and this quality of energy leads to the exergy analysis, and the exergy is defined as the maximum obtainable work for a given environment. When environment changes, this obtainable maximum obtainable work also changes. And we do exergy analysis based on second law of thermodynamics. Okay, so it is correct answer. And the next question is next and the final question for this session is, in an impulse reaction turbine stage, okay, the heat drop in fixed and moving blades are 30 kilojoule and 40 kilojoule respectively. The degree of reaction for this stage will be, okay. So here in the question we are talking about impulse reaction turbine. So that means simply reaction turbine we are talking about. And for this reaction turbine, the heat drop in fixed and moving blades is 1340 kilojoule. So the heat drop del H in fixed blade FB is equal to 30 kilojoule, and del H moving blade MB is equal to 40 kilojoule. Okay, so these two heat drops are given and the degree of reaction is asked. So the degree of reaction R is del H moving blades divided by del H fixed blade plus del H moving blades, right? So here del H moving blade is 40 kilojoule and del H fixed blade is 30 kilojoule and 40 kilojoule. So that means 40 kilojoule by 70 kilojoule. So degree of reaction is 4 by 7. Okay. So this is again a very simple problem, and this is the answer. Okay. Okay. I hope you understand till here. Uh, okay. So any questions till here? No. Okay. So now let's see what is Vicky asking. So the saturated steam is at 600 K and 135 bar pressure when it enters to the turbine, and the condensing temperature is of 300 K, and the pressure is this. Calculate the efficiency of power plant considering an ideal regenerative Rankine cycle. Okay. So Vicky, what is the doubt in this question? Like, do you have any specific doubt at a specific stage, or like the whole question is the doubt? You can unmute yourself and ask the whole question. Okay. So we do something. Okay. So in that case, I won't waste the time of other fellows, but I will solve this question and send you the solution. Okay, that works for you, Vicky? Or what we can do is I will send you the solution, and if you still have doubt, then in the next session we can discuss. That works for you? Okay. Okay. So please mention your email ID here. Okay, I will email you the solution. Yeah, I will send you the solution. You write your email ID here. Okay. And any doubts still here? Anything, if you want to ask, you can ask now. And from the next session, I think we will discuss about the, I think, power cycles, not gas power cycle. Okay, yeah. So gas power cycle we will be talking about in the next session. So okay, if you don't have, yeah, ice engine, yes, yes, ice engine. So if you still have any doubt till here in the last three sessions, you can ask, you can write me. Okay, if you have any doubt, if you want, we can arrange a separate session to clear your doubt. If you need and you want, we can do that. So yeah. Okay, so for today's session, we will stop here, and see you guys in the next session.